Hello, continuing. Now we're going to look at a area and volume type question that involves tolerances or accuracy. So I have a triangular or an inverted triangle type shaped trough that it might be used to hold water for animals. And it is 0.5 meters wide, 5 meters long, and 0.1 meters or 10 centimeters high. So from the top piece to the very bottom tip is going to be 0.1 meters tall. And we're assuming it starts from empty and the trough is filled at a rate of 1 liter per minute, correct to the nearest 0.2 liter per minute. Find the max time to fill the trough if the measurements are made in decimeters. So here we have to figure out if we're increasing the volume of water in the trough at a particular rate, we need to know the volume of the trough in order to find out how long it's going to take to fill the trough. That part is fairly self-explanatory. What we need to keep in mind, however, is that we're given two extra pieces of information. We're told the accuracy of the measurements in both cases, and we need to take them into account when we're doing our problems. We're told we're going correct to the nearest 0.2 liter per minute. That is an accuracy indicator. We are measuring correct to a particular count, to a particular decimal. And here we are told that our length measurements are done in decimeters. That is tenths of a meter, or 10 centimeter increments. So we have been given accuracy information. And that's the first thing we're going to have a look at, and then we're going to figure out how to solve the problem. But if we're told that we have an accuracy of 0.2 liters per minute, that means that if we say, if the measurement was measured as 1 liter per minute, we'd be judging halfway, or potentially judging halfway between our markers of 0.2. So we'd say we can judge halfway between our markers pretty accurately. So that means that our tolerance would be half of this, because we can fairly accurately judge halfway between any marker that we've got. So if we were measuring in centimeters, we're pretty good at judging in plus or minus half a centimeter on our measures. And this is a pragmatic type thing. This is not kind of a fundamental definition. This is just what we take in practice for taking measurements. If we have markers every 0.2 liter per minute, then we say that our tolerance would be half of that unit. If we were measuring that flow rate, it would be plus or minus half of that, which would be half of 0.2 would be plus or minus 0.1 liters per minute. Likewise, we have an accuracy given in decimeters, which would be 10 centimeters. So an accuracy of 10 centimeters is a more familiar unit to us than decimeters. So our metal was cut out to an accuracy of 10 centimeters. We were just looking at our 10 centimeter marks on our ruler. And we're going to say then that our tolerance for that would be plus or minus half of it. Would be plus or minus 5 centimeters, which would be plus or minus 0.05 meters. So, given the accuracy of the measurements we're told about, our flow rate could be anything between 0.9 liters per minute and 1.1 liters per minute. And our measurements, say the length of our trough, could be anything from 4 meters and 95 centimeters up to 5 meters and 5 centimeters. So that's the fluctuations we can have within our measurements based on the accuracy that we're told about. And this is a common thing. Anytime we're given a measurement, our tolerance would be plus or minus half of the unit we are using to measure with. So let's put this into practice now. We want to know the maximum time that it might take to fill this trough. Well, this is a purely reasoning question. We have to think about physically what would happen to maximize the time that it would take to fill the trough. Well, if the trough was bigger, it would take longer to fill. And if the flow rate was slower, if the water was coming slower, it would take longer to fill. So the maximum time to fill up our trough is going to happen when we have the biggest possible container filling at the slowest possible rate. So what we're interested in is the maximum volume and the minimum flow. We want both of those things. And if we have both of those things, then we're going to have our situation where we take the maximum amount of time to fill up our trough with water. So our minimum flow rate, we may as well go with, is going to be, so our minimum flow rate is going to be our 1 liter is our measured, minus, we're going to slow it down as much as we can within our measurement, so that's going to be minus 0.1 liters per minute is 0.9 liters per minute. But we know that we want to work in meters in this case. So a liter is a measurement of volume, but it's not a particularly convenient measure of volume. Call that min. So we want to have our flow rate in meters cubed so that we are dealing with everything in the same units. This is critical. If we don't do this, we'll get entirely the wrong answer. So how are we going to go from liters to meters cubed? Well, a liter is a decimeter cubed. It would be 0.1 of a meter by 0.1 of a meter by 0.1 of a meter, or a tenth multiplied by a tenth multiplied by a tenth. So a liter is equal to 1 decimeter cubed, which means that which would be a tenth of a meter by a tenth of a meter by a tenth of a meter would be 1,000 of a meter cubed. Each one of our dimensions is in tenths of meters, so we would multiply them all together to get the equivalent volume. So our 0.9 liters per minute would be 0.9 over 1,000 meters cubed per minute. So our minimum flow would be 0.9 all over 1,000 meters cubed per minute, which you can just write as 0.0009 meters cubed per minute. And now we've got our minimum flow rate. Now we need to figure out what our maximum volume is. How big could that trough possibly be based on the accuracy of the measurements that we have been given? So volume max. Well, let's redraw our object here. I have drawn the first triangle a little bit high there. So we have our maximum height would be 0.1 meters plus our 5 centimeters. So that would be 0.15 meters. Our maximum possible length would be 5.05 meters. And our maximum width would be 0.55 meters. We've added on 5 centimeters in each case. That's the maximum possible dimensions that we could have ended up with based on the accuracy of the measurements we are told about. So our volume then, we have to recognize what type of shape we've got, and this is effectively is a triangular prism. We have a triangular face on the end, and it continues parallel back from that. So just like a cylinder is a circle multiplied by the height of the cylinder, this is going to be a triangle multiplied by the height of the cylinder. So our volume is going to be the area of this end triangle, which is going to be half the base by the height multiplied by the length of our trough. Vmax is going to be a half the base by the height. Base we'll say is 0.55. By the height is 0.15. By the length of our shape is 5.05. When we put that into our calculators, we get 0.2083 meters cubed. And we go to 4 decimal places in the middle of a question like this. And at the end, if we're not asked anything, we'll go to 2. Now, how are we going to get this? This is our maximum volume of our trough. And then this is the flow rate, how many meters cubed are going into our trough per minute. So if we divide those, to get our time is going to be our volume all over our flow rate. It's going to be 0.2083 all over 0.0009. Ends up being equal to 231.4583, which will round to our nearest minute, 231 minutes. So 231 minutes would be needed in order to fill up our trough. So what steps did we take here? We figured out what our tolerance was based on our accuracy, so plus or minus half of the units we're measuring in. Then we worked out by simply arguing it out for ourselves what would take the longest time if our volume was max and our flow rate was min, or as slow as possible. Then we worked out our flow rates and had to convert from liters to meters cubed. And then we got our volume, and if we divide the volume by how much volume is being added each minute, we are going to get our number of minutes needed to fill our trough. And that is what we need for now.